In today's video, we're going to talk about the periodic table. And this is a list, kind of all the elements that are present. You've probably seen this before in maybe a previous science class. It looks like this, and there seems to be some structure to it. So it's not just a list of elements. There's also some other information that's given in the structure of what this table looks like. So I'll give you a little hint at some of that information now, and as the year goes on, you'll learn more and more about why the periodic table is organized the way it is. It actually makes a lot of sense. On the periodic table, each element has a unique symbol that's unique to that element alone. This symbol will be either 1 or 2 letters long. In the case that it's 1 letter long, there will be just a capital letter. If it's 2 letters long, the first letter is always capitalized, like we see here in lead. The P in PB is capitalized, and the second letter is always lowercase, like we see in this example. And bismuth, same thing, capital B, small I. It's important to make sure that you always write uppercase first letter, lowercase second letter. Even if, like me, you usually don't use lowercase letters and just write everything out in block caps, you should not do that when you're writing elemental symbols because it's confusing. Let me give you an example. Cobalt is capital C, small o. If I wrote that capital C, capital O, that's not cobalt anymore. That's now a compound called carbon monoxide. So follow the rules here to avoid confusion. The elemental symbols that you'll find on the periodic table come from 3 primary sources on our periodic table. One is English names, and I've got 3 examples over here. S is an abbreviation for sulfur, C is an abbreviation for carbon, H is an abbreviation for hydrogen, and a lot of the periodic table symbols come from English names. Some of them, if you're looking for an English name, you won't find it. It won't make any sense. And in many cases, that's because they come from Latin names, abbreviations for the Latin names for those elements. Like iron is not I or IR, it's Fe, which is short for ferrum. And copper is Cu, which is short for cuprum. And sodium is Na, which is short for natrium. Those are all Latin names for the elements that we know as iron, copper, sodium. And there are quite a few of these on the periodic table. And then there's one that comes from a German name on our table, and that's W, which is short for wolfram. Wolfram is the German name for what we call tungsten. So how is the periodic table organized? Well, the vertical columns in the periodic table are called groups, or sometimes they're called families. The reason that they're called families is because members of a group or members of a family have similar properties. Let's think about it this way. The halogens are the column that has fluorine, chlorine, bromine, iodine, and astatine in it. These things all are very reactive. They all smell kind of the same. They smell a little bit like bleach, which is chlorine in it. And they're all gases or very near gases. Now that doesn't mean they're identical. They aren't. Just like you and your brothers and sisters aren't identical, but you do have some features or characteristics that sort of tie you together. They're similar. The horizontal rows on the periodic table are called periods, and that's where periodic table comes from, because every so often, every period, it repeats. Members of a period are not like families. In fact, they're often very different from each other. For example, if I take a look at sodium here, and I click on it, I get a picture of what sodium is like. It's a silvery metal. It turns out to be extremely reactive. When it reacts with water, it makes something called a base. On the other hand, if I click on chlorine, I'll get some information about it. And it's not a metal, and it's not silvery, it's not even a solid. It's this pale yellow-green gas that you see right here. It's also very reactive, but when it reacts with water, it doesn't make a base. It makes something called an acid, which is just the opposite of a base. So in the same row, you are not going to find similarities necessarily. But in a vertical column, in families, you would find some chemical and sometimes physical similarities. In the periodic table, another part of its structure is that there's this major division in the periodic table. The elements boron, silicon, arsenic, tellurium, and astatine are part of this division. If I were to draw a stair-step line that goes right under these elements, boron, silicon, arsenic, tellurium, astatine, that stair-step line is a boundary. It's a major division on the periodic table. The elements that lie to the left of those elements on that boundary are called metals. So over here, these are called the metals. Now, this is going to include aluminum, that's here, and polonium, which is here, but not the Ge and the Sb, germanium and antimony, that touch the line. So aluminum's a metal, polonium's a metal, but Ge and Sb are not. Here's what metals are like. They have some properties that make them identifiable. One is that they're malleable and ductile. Malleable comes from the same word root that mallet comes from, and a mallet is a hammer, and that gives you a clue of what it means. You can bang on these things and they will smush into different shapes. Like if you pound on a piece of gold or pound on a piece of lead, you can make it into a different shape. And ductile means they're stretchable, and you can actually take metals and stretch them out. That's how they make wires, and it's often how they make things like cans. Here's an example of ductility shown in this picture here. This large bowl here is being spun. It started out as a flat sheet, and it's being thinned out, stretched, and it's being formed by spinning it around and around, almost like a pottery wheel. You couldn't do that with non-metals. They would just break. They're stretchable, and they're poundable. They're formable. Another characteristic of metals is that they're shiny. This property is seen here in these metallized skyscraper windows. Metals reflect lots of wavelengths of light. In fact, most metals reflect so many wavelengths of light that they are mirror-like. You see all the colors. Not all of them. Copper and gold are exceptions, but most metals are very reflective. They tend to be very good electrical conductors, and so you see in these wires here that there are copper strands that are carrying electrical current. That's why we use metals to wire our homes and to make battery terminals. Any place where electrical conductivity is needed, you want to use a metal, typically. Metals are also very good heat conductors. So if you want to move heat energy from one place to another very effectively, you would use a metal. So here in this picture we have several pots that are all made of iron, probably. Iron is a metal, and as a metal it's a very good heat conductor. Back to our division in the periodic table, the elements that lie to the right of the division elements are called non-metals. So their name sort of implies that they just aren't metals, and their properties reflect that as well. Here are the properties of non-metals. Every one of them is like the exact opposite of what metals are like. Non-metals tend to be brittle. In other words, if you try to stretch them, bend them, form them, hit them with a hammer, they're just going to break. An example would be the pencil lead that we see in this picture. Pencil lead is carbon. Carbon is a non-metal, and it's brittle. It's not ductile. If I tried to stretch it, try to pull on it, it won't stretch, it'll just break. If I try to bend it, which I could easily do with copper or gold or aluminum, it will just snap. So they're brittle. They also tend to be dull in appearance. When you look at them, they're not shiny at all. This is a sample of some iodine, which is a non-metal, element I. And you can see that it doesn't reflect light very well. Charcoal, which is carbon, is another good example of a dull appearing non-metal. Lots of the non-metals we can't see in everyday daily life because they happen to be gases at normal temperatures. Whereas metals are good electrical conductors, non-metals are poor electrical conductors. So in these wires, where we want the electricity not to be conducted on the outside of the wire, we put a coating of non-metals. These plastics are made of non-metals, and they're good at insulating. In other words, they're not very good at conducting electricity. Non-metals also tend to be very poor heat conductors. In this house, you can see that they have a lot of windows. Those windows would conduct a lot of heat typically, except they're made of glass, and glass is mostly of non-metals. And very efficient windows have two layers of glass, and in between is an inert gas, and those gases are non-metals. And because they're bad at conducting heat, that makes them even more efficient at keeping the heat in. Now looking back at our chart, we notice that we've identified the metals, they're to the left of the line, and the non-metals are to the right of the line, but we haven't said anything about the elements that actually touch that line. Those elements have a name too. They're called metalloids. Everything that touches that stair-step line, with the exception of aluminum and polonium, which is rare, is called a metalloid. Or sometimes these are called semi-metals. Semi is a word that means half, so they're like half metal. What does that mean? Well, their properties, just like their position on the periodic table, is in between metals and nonmetals. Sometimes they're like good conductors of electricity, and sometimes they aren't. Sometimes they behave like metals, sometimes they don't. Well, that makes them fairly useful. And one of the most useful of these things is silicon. Silicon is used in computer chips because engineers have figured out how to make very small collections of silicon atoms function as switches, because you can make them, depending on the conditions, function either like an on switch, a conductive material, a metal, or an off switch, an insulating material like a nonmetal. On the periodic table, there are some important groups that we want to sort of identify. One is the alkali metals. The alkali metals do not include hydrogen. Hydrogen's up at the top here, but that is not a metal. That actually belongs over here with the nonmetals. So starting below that, we have lithium, sodium, potassium, rubidium, cesium, and francium. These alkali metals are extremely reactive, and so you almost never find them in their pure form. When you do, it's because someone has gone through a great deal of trouble to keep them separated from other elements, because they'll react immediately and form compounds. Two famous ones are sodium and potassium. When sodium and potassium are put in water, they react really violently to produce something called a base, but they also produce hydrogen gas, which is extremely flammable. So if this is happening in an open environment where there's oxygen available, they can ignite and produce water, and it's a very explosive reaction. What makes it even more exciting is that the reaction also produces enough heat to ignite the hydrogen and oxygen, so that can be kind of fun and dangerous. Here you can see one of the many doofuses on YouTube dropping sodium in a bucket of water. Very violent reaction. The group that's second from the left is called the alkaline earth metals, and this includes beryllium, magnesium, calcium, strontium, barium, and radium. And you've probably heard some of those names before. You know that calcium is in your bones probably, but did you know it was a metal? You don't think of your bones being made of metal, but there's a lot of calcium in your bones, and it's part of compounds, but that's what it is. These things are pretty reactive, but they're a little more stable than the alkali metals, and so you can't just throw them into water and have these violent reactions take place. Another group isn't really a group, it's a kind of a collection of groups. If you made a triangle that started here at scandium and went over here to zinc, and then went down to mercury, and then went back over to lanthanum, this whole group in here, this rectangle, these are called the transition metals. And the transition metals are the metals that you think of when you think of metals. So things like gold and silver and copper and titanium and iron, those are in this cluster. It also includes these two groups down here at the bottom, which are called the lanthanides, that's the first row, and the actinides, that's the second row. The halogens are another important group. They're the group that is the second from the right on the periodic table, and this includes fluorine, chlorine, bromine, iodine, and astatine. Those are the elements that we call the halogens. You notice that they all end in -ine. They're also highly reactive. So the things closer to the outside of the table are the most reactive. Things closer to the middle of the table are more stable, with one exception that we'll talk about in a bit. Because they're so reactive, they're rarely found in their pure form. Most of the time they exist as part of what we call a salt. So halogen, literally the word parts that it comes from, mean salt former. That's what these things do. They find metals actually and form salts. And they all have a characteristic odor. They all smell like bleach. Chlorine is the thing that we think of as smelling like bleach, but all of these halogens have that smell. The last group we're going to look at is called the noble gases. The noble gases are the column that's farthest to the right. They get their name from the fact that they are like standoffish. They don't get involved with other things like noble people would have back in the old days. Another name for them is inert gases. And inert is a very descriptive word. They are inert, which means they don't react with things. They will, but you have to really force it to happen. So most commonly these things are found in their pure form, because they're so unreactive. Often they're found in air because they're all gases. Here's what they include: helium, the squeaky voice element; neon, that you'd find in neon signs; argon; krypton, yeah, it's real, it's not just in Superman; xenon; and radon. Radon is found in a lot of older homes and has been connected to lung cancer. Because they're so unreactive, they have a lot of uses in keeping things from reacting, like shielding gases in welding. When you want to get something hot but not have it catch on fire, you can flood the area with a noble gas, and that'll stop reactions from occurring. Light bulbs contain argon typically, and that keeps the filament from reacting with air and burning up. So this gives us a look at the basic structure of the periodic table and some of the important groups that are on the periodic table. We'll come back to the periodic table again and again and again because it's such an important document. And as I said earlier, it's not just a list of elements. There's a lot of structure there that tells a lot of stories about how the elements react with each other and what their properties are.